Chapter 2, Section 7, Physics Talk, Forces Affecting Collisions. By examining the different crumple zones designed by other teams in your class, you can get an insight into the physics of collisions. Probably no team just used the flat sheet of paper. Most teams tried to fold the paper in specific ways. It seemed the goal was to have a softer collision rather than have the cart hit the wall without any crumple zone. By trying to make a softer collision, you may have used the physics of work and change in kinetic energy. Work equals force times distance equals change in kinetic energy. In this case, as in the airbag, you wanted to decrease the force by increasing the distance to stop the automobile. The work done on the cart then reduced the kinetic energy of the cart. Impulse and changes in momentum. There is an equivalent way of describing the physics of a collision. Rather than focusing on the distance that the force acts, you can look at the amount of time that the force acts. By maximizing the time, you can minimize the force. When creating the crumple zone, you increase the time and thereby minimize the force. It takes an unbalanced opposing force to stop a It takes an unbalanced opposing force to stop a moving automobile. Newton's second law of motion, force equals mass times acceleration, lets you find out how much force is required to stop any automobile of any mass with a corresponding acceleration or change in speed with respect to time. For example, if a 1,000 kilogram automobile accelerates at -2 meters per second squared, then the force required is force equals mass times acceleration, which equals, so now we're taking mass times acceleration to figure out the force. So we're taking 1,000 kilograms, which is the mass, times -2 meters per second squared, and then you're taking equals -2,000 newtons. So the force equals -2,000 newtons. Notice that the acceleration is negative because the automobile's velocity decreased. Also notice that the force is negative to indicate that it produces a negative acceleration as it slows the automobile down to a stop. The overall idea can be shown using a concept map seen at the top of the next page. Okay, so let's look at this concept map. Force equals mass times acceleration. Okay, so that's force equals mass times acceleration, where F is force, M is mass, and A is acceleration. Where acceleration equals change in velocity divided by change in time. And change in velocity equals your final velocity minus your initial velocity. All right. If you know the mass and can determine the acceleration, you can calculate the force using Newton's second law, which is force equals mass times acceleration. All right, suppose a moving automobile has a forward velocity of 15 meters per second. Stopping the automobile in 3 seconds gives it a final velocity of 0 meters per second. The change in velocity is your final velocity minus your initial velocity, which is 0 minus 15 meters per second, which is -15 meters per second. This calculation corresponds to the bottom box in the concept map. Okay, so let's scroll back up to the concept map. Okay. This calculation corresponds to the bottom box. Here's the bottom box in the concept map. Any change in velocity is defined as acceleration. In this case, the change in velocity is -15 meters per second of acceleration, which is a deceleration. A deceleration is the same as a negative acceleration. And acceleration is the same as a positive acceleration. All right, guys. If the change in velocity occurs in 3 seconds, the acceleration is negative 15 meters per second in 3 seconds, or negative 5 meters per second every second, or negative 5 meters per second squared. You can look at this as an equation. Acceleration equals change in velocity over change in time. Final velocity minus initial velocity divided by change in time. Now you have calculated your change in velocity, you've calculated your change in time. So you take your negative 15 divided by 3, and that equals negative 5 meters per second squared. This calculation corresponds to the upper right corner in the concept map. So right here, this calculation corresponds to the upper right box, which is acceleration equals change in velocity divided by change in time. All right. That was the upper right one. Okay, so now we're on this one. Newton's second law informs you that unbalanced outside forces cause all accelerations. The force stopping the automobile may have been the frictional force of the brakes and tires on the road, or the force of a tree, or the force of another automobile. Once you know the acceleration, you can calculate the force using Newton's second law. If the automobile has a mass of 1,000 kilograms, the unbalanced force for the acceleration of negative 5 meters per second every second would be negative 5,000 newtons of force. The negative sign tells you that the unbalanced force was opposite in direction to the velocity. If the automobile has a mass of 1,000 kilograms, the unbalanced force for the acceleration of negative 5 meters per second every second would be negative 5,000 newtons. Force equals mass times acceleration. So if you have a mass of 1,000 kilograms and an acceleration of negative 5 meters per second square, then you get negative 5,000 newtons. The same problem can be solved with the same automobile stopping in a half of a second. The change in speed would still be negative 15 meters per second, and the acceleration can be calculated. Initial velocity minus, okay, and then so basically you're just doing the negative 15 meters per second squared divided by a half a second equals negative 30 meters per second squared. And a lot of this stuff, if you need one-to-one support, you can contact myself, you can contact Miss McEntee. We can definitely provide one-to-one individual support. This is really the asynchronous time, and then we can definitely provide synchronous support, whether that's during the regularly scheduled time or really any time that's convenient for you. Just let Miss McEntee or I know, and that's what we're here for. We're here to support you on this. Okay, so moving along, there's another equivalent picture that describes the same collision. Force equals mass times acceleration. Multiplying both sides of this equation by changes in time, you get force times the change in time equals mass times the change in velocity. Then you can rewrite Newton's second law as force equals mass times the change in velocity divided by the change in time. We're right here. The term on the right-hand side of, I need to scroll up. They're talking about the equation. The term on the right-hand side of the equation is change in momentum. The term on the left side of the equation is impulse. Any moving automobile has momentum. Momentum is represented with a small p. Momentum is defined as the mass of the automobile multiplied by its velocity. Momentum equals mass times velocity. A change in momentum is called impulse. The impulse momentum equation tells you that the momentum of the automobile can be changed by applying a force for a given amount of time. The impulse is the force multiplied by time. So a small force exerted over a long time produces the same impulse or change in momentum as a large force exerted over a short time. The small force exerted over a long time is what you found in the effective crumple zones. Impulse momentum is an effective way in which to describe all collisions. Consider this question. Why do you prefer to land on soft grass rather than on hard concrete? Soft grass is preferred because the force on your body is less than when you land on soft grass. I'm sorry. Soft grass is preferred because the force on your body is less when you land on soft grass. This can be explained by using the impulse-momentum relation. Whether you land on concrete or soft grass, your change in velocity will be identical. Your velocity may decrease from 3 meters per second to 0 meters per second. On concrete, this change occurs very fast, while on soft grass, this change occurs in a longer period of time. Your acceleration on soft grass is smaller because the change in velocity occurred in a longer period of time. Acceleration equals change in velocity over change in time. Kind of similar how speed equals miles per hour or kilometers per hour, but here you're having acceleration equals change in velocity over change in time. All right. When the change in the period of time gets larger, the denominator of the fraction gets larger, right here. And the value of acceleration gets smaller, right here. When landing on grass, Newton's second law then tells you that the force must be smaller because the acceleration is smaller for an identical mass. Smaller acceleration on grass requires a smaller force. Smaller forces are easier on your body, and that is why you prefer to land on soft grass. All right. Change in value of momentum. Remember, guys, that small p is momentum. So change in momentum equals a change in mass times a change in volume. All right, so you've got a chart where it's showing this equation. Here's your momentum. Well, here's your change of momentum. Here's your force. Here's your change in time, and here's your impulse. You can get this change in momentum with a large force over a short time or a small force over a longer time. If your mass is 50 kilograms, the amount of your change in momentum will be 150 kilograms times meters per second when you decrease your velocity from 3 meters per second to 0 meters per second. There are many forces and associated times that can give this change in the value of momentum. If you could land on a surface that requires 3 seconds to stop, it will only require 50 newtons. Here it is, guys. If you could land on a surface that requires 3 seconds to stop, so we're using the chart, so look for 3 seconds right here. It will only require 50 newtons. How do we know that? Because we found 3 seconds on the chart, and there's 50 newtons right in the same row. All right. A more realistic time of 1 second to stop, right here, will require a larger force of 150 newtons. How do we know that? We looked at 1 second, and there's your 150. Oh, I'm sorry. We looked at 1 second, and there's your 150 newtons. A hard surface that brings you to a stop in 0.01 seconds, or 1/100th of a second, requires a much larger force of 15,000 newtons. How do we know that? Here's your change in time. Here's your force. On concrete, this change in the value of the momentum occurs very fast and requires a large force. It hurts. On soft grass, this change in the value of momentum occurs in a longer time and requires a small force that is less painful and is preferred. Notice that in the chart above, the change in momentum is always equal to the impulse. Okay, so we're kind of bridging over this way. All right. Work and energy, or impulse and momentum. The effective crumple zone decreases the force on the passenger. Using the work-energy theorem, the force can be minimized by increasing the distance required to stop. Using the impulse-momentum theorem, the force can be minimized by increasing the time required. As a physics student, it is your job to decide which of these two approaches is best for explaining a particular collision. Work equals force times distance equals the change, or force times the change in time, or I'm sorry, force times the change in time equals the change in momentum. Both show that the force can be minimized. In work energy, force is minimized by an increase in impact distance. In impulse momentum, force is minimized by an increase in impact time. Conserving momentum. Conserving momentum. In Part B of the Investigate, a moving cart was brought to rest. The moving cart had momentum. The force probe was able to record the force that was applied to the cart over time to stop the cart. This force over time changed the momentum of the cart. The force first time graphs for two carts with the same initial momentum are sketched below. As you can see, so let me scroll down. So we're looking at these graphs. As you can see, the cart with the hard cushion had a larger force acting over a shorter time than the cart with the soft cushion. For the safety of passengers, a small force over a long time is what is needed. So this is for the safety of passengers because it lessens your force. The force is what's going to hurt your passengers. So this lessens the force by having this soft cushion, where if you have a hard cushion, you're way up here. This is the injury zone. This is the zone that could cause injuries or cause loss of life. Whereas with a soft cushion, you're really softening that force over a longer period of time. You're lessening that force. All right, so where were we? Designing a safety device for an automobile is often determined by finding ways to decrease the force and increase the time during an impact. The change in momentum of a cart or an automobile can be identical, but a smaller force over a larger time will be safer. You know that during a collision, momentum is always conserved. However, confusion may arise because now you find that a force can change the momentum of a cart by bringing it to rest. How can momentum be conserved in collisions, but momentum can be changed by a cushion? It may help to view the collision from two different perspectives. It is true that the total momentum before the collision is equal to the total momentum after the collision. However, during the collision, the first cart may lose momentum while the second cart may gain momentum. Each cart changed momentum, but the total momentum remained the same. A similar thing happens when the force probe stops the automobile. The automobile loses momentum. The probe gains that same amount of momentum. Since its mass is large, it is connected to the lab table. Then this large gain in momentum corresponds to a very small gain in velocity. You may recall that another way in which to describe the same cushion is to say that the larger force is acted over a shorter distance. The work done by the force over the distance was the same for both bumpers, and both bumpers decreased the kinetic energy of the automobile. Change in momentum and impulse. Momentum is the product of the mass and the velocity of an object, where P is the momentum, M is the mass, and V is the velocity. Change in momentum is the change in the product of mass and velocity. If the mass remains the same, the change in the momentum is the product of the mass and the change in velocity. Momentum equals change in mass times change in velocity. Impulse is the change in momentum. So your force times the change in time equals the change in the mass times velocity. Change in kinetic energy and work. Kinetic energy is the product of half the mass and the square of the velocity. Kinetic energy equals 1/2 of the mass times velocity squared. Work is the product of the force and the distance over which the force acts. Work is equal to the change in kinetic energy. Work equals change in kinetic energy.